Hello. Hello.
You should be the host now.
Okie doke. All right, is everyone able to see my screen and hear me all right? All right. Let's see, how many do we have? 16. Okay, we've got enough to go ahead and get started. Okay, so today we are going to be talking about probability. Specifically, we're going to be talking about causality, simulation, and probability. Being able to run experiments on the computer. Those are the simulations we're talking about. So let's talk about using Python for these simulations. What is Russian roulette? It is a lethal game of chance in which a player places a single round in a revolver, spins the cylinder, places the muzzle against their head, and pulls the trigger and hopes that the loaded chamber does not align with the primer, percussion mechanism, and barrel, causing the weapon to discharge. Russian refers to the supposed country of origin, and roulette to the element of risk-taking and spinning of the revolver cylinder, which is reminiscent of spinning the roulette wheel. So you have a cylinder that has 6 chambers in it. You put 1 bullet in there. You spin it to randomize the configuration and hope that the chamber that comes up to the barrel is empty. That's kind of how you play. You can take my recommendation and don't play it. So let us simulate a game of Russian roulette. Here's the interesting thing, at least to me. Russian roulette and throwing out, getting 5 cards from a deck and the ace of spades, shuffling those 6 cards up and trying to draw ace of spades off the top. That's the same game. It's the exact same game, except for the, outcome of what happens. In that you have a 1 in 6 chance in a completely randomized list of stuff, and each time you draw a card or pull the trigger, you are playing the same game. We can simulate either of those things with the following. We're going to say a NumPy array looks like this. It's got a 1 and then 5 zeros in sequence. What we're going to do is we're randomly going to pick from our list. Now, you can see this takes an argument here. Selecting 1. If I play this long enough, eventually I'm gonna come up with the bullet. There it is. I didn't count how many times that took, but, or I could put in 5. I'm selecting 5. This is kind of like playing the inverse. Well, that's not true. When we put the number here, as you saw, here, I'll do it again. This isn't spin the cylinder and then pull the trigger 5 times. because if you were to spin the cylinder and pull the trigger 6 times, you would get the one round that has the bullet in it. But no, this is run the experiment 5 times is what it's doing. So if I run the simulation once, what are the odds of me getting the bullet? It's 1 in 6. If I run the simulation twice, what are the odds of me getting at least one bullet? Do some statistics stuff here. There's a nice formula for that. But here's the way I like to look at it. I think so. If you have events that are, there's a term for it. It's called independent and identically distributed. One moment while I dog out. What that means, independent, is that one does not have an effect on the other. So running one simulation doesn't affect running the next simulation. And identically distributed means it's the same simulation. So if you have those two conditions, then you can do this. Well, I view this, I didn't come up with this name. I view experiments like this as possible worlds. Before we run anything, we have the possible world that we're in. There's only one. And so what's the outcome? What is the likelihood that we're in that world? It's 1 out of 1. You count how many there are. You count how many the particular thing occurring is in, and then you divide those two. So you get 1. Well, with the revolver, I should change color. This will work. There's 1 bullet and there's 6 cylinders. Each of these are equally likely. So what is the likelihood of me ending up in the red one, the one with the bullet? Well, there's 1 of them. There's 1. And there are 6 total outcomes. So 1 in 6. So then I asked, what if we did it twice? Well, we just run the same experiment again. And so that will get us, I'm not going to draw them all out from here because there's not enough space. So we get 1, 2, 3, 4, 5 of those, and 1 of these. Believe it or not, this may look like teaching like 5th graders or something, but this is really the theory behind at least a couple solvers that that do this stuff. So now we had 1 in 6 chance of getting here. Well, what's the total chance of having it happen again? Well, without even having to do math, each of these spots has the same thing coming out. So how many worlds are there on this second level here? Well, there's 6 from this one, there's 6 from this one, 6 from this one. And that will let you count up how many there are. If you, it can be any kind of experiment, not just the Russian roulette. All right, so enough of that. What's the likelihood of us at least getting the bullet once if we pull the trigger 10 times? It's quite high. We only got it once. That's pretty good, I guess. There's a little comic about it that I like. So as I was saying about drawing the cards, that is the same experiment. So is throwing a d6. So a d6 is a regular die, kind everybody's used to. Instead of just leaving the sides as zeros, we're going to label them all as what their particular face is. Now, the reason this is the same experiment is that in this one, we cared about the, let's call it the face with one pip, and then the rest of them we just didn't care about. But everything else is still the same. All right, so let us put in a die, and then we're gonna roll it 10 times. So this is the result of randomly choosing from our NumPy array 10 times, also known as throwing the die 6 times. Now, all right. What I was thinking of doing, we're already going to do here. let us make something a little more interesting with this D6. We're going to have a game. So if you throw the die and you get a 1 or a 2, then you lose $1. If the die shows 3 or 4, your net gain is $0. So you just break even. If the die shows 5 or 6, you get $1. So this is a good time for me to bring up the term expected value. And the formal definition is a little different, but what it means is exactly how it sounds. So can someone answer me? So expected value is, given a simulation, what is the value you expect to see in average? So what, in dollars, what would you say the expected value of this game is? Right, so Parth says 0. That is, that's true. It's pretty easy in this case to calculate the expected value. How many cases are there for losing $1? There's 2. How many cases are there for gaining $1? There's 2. They kind of cancel each other out. How many cases are there for losing 0? It doesn't really matter. You could just average them all up. Just, -1, -1, 0, 0, 1, and 1 divided by 6. You get 0. Every random event like this has an expected value. Just like the state lottery has an expected value. The thing about, and going to the casino has an expected, well, the games you play have expected values. The thing about it, though, is that the casino wouldn't be in business, the lottery wouldn't be in business, if everything was just 50-50. If everything's 50-50 and I don't cheat, then I'm not making any money by putting up all these machines and stuff. So this is, when you look at blackjack, as long as you don't cheat, it's kind of a fair game, right? Well, the expected value is slightly shifted towards the dealer. I forget the exact number. I didn't prepare it. It's small, but something like 51 out of 100. I think it's closer to like 53 out of 100. But over time, that means that you're making money rather than losing money. But you as the player, eventually, if you don't do something clever like count cards, then you're going to be losing money. Where this comes into something I think is interesting, consider the state lottery. The expected value of you playing the lottery, you have to calculate it. Assuming that there is one winner. Or actually, you don't even have to make that assumption. But the thing about the lottery is that the jackpot hits a number where the expected value shifts from negative to positive. And a lot of people who know that will, have like $10, $50 lying around. And the moment that number, the jackpot changes to that number, the expected value is no longer negative. They'll just go and buy that many tickets. Funny enough, the entire government, well, like the entire country, I guess, of Australia decided to do this 20, 30 years ago. They waited till, I don't remember which state it was, but some lottery in the US. They waited until the expected value shifted to be positive, and then they just dumped a whole bunch of money into it, and they got more money out than they did. After that, they had to make a law saying that foreign bodies can't buy lottery tickets. But yeah, expected values. All right, so we have a game here that is encoding the rules we have. And the way it works is I'm going to roll as many times as I say here with the number, and then we're going to play the game that many times. All right, so play 5 times. Well, it looks like overall I lost. Let's play it 50 times, see what happens. It's pretty close to 0 considering we're doing it 50 times. 6, 2. Now, here is what is should be noted about what we've got going on here. One simulation of doing this in this cell we have here is playing the game 50 times. It's called, that's the simulation, 50 attempts of playing the game. Now, what we can do is what, range 0, 6. We run this simulation a couple times. All right, it won't the print. And this is now an experiment, just slightly different terms, but we're doing the simulation of rolling the D6 50 times. And now I'm saying do that, 6 times. What's worth noting about it is that because we know that the expected value is 0, is if we plot out kind of where, so this will be 0 right here. No, I don't want that one. So this will be 0. This will be like, just that's the negative and it's the positive, right? What we should see is a lot of values. So I'm going to run this experiment, I don't know, 10 times. What we should see are lots of values in this area right here. Seeing values that are like further this way, like -50, that should be rare. Why? Because what that would mean, since we're doing rolling the D6 50 times, that means you got the 1 1/3 chance of losing the dollar 50 times. So what this turns into is a distribution like this of what your total net is. Now, what I can do is I can change the experiment. So instead of making the 5 or 6 let you gain $1, what I'm going to do is I'm going to make this only a 6 gets you $1. So if I've made the 3, 4, and 5 break even. So now what we should start to see is much more, and we'll see it even more with the 500, is everything is going to be more negative because there's only one case to gain $1. I need to actually run it. And so everything's negative here because I did it 50 times. If I do it 5 times, well, heck, let's just start with 1. The smaller the number in my simulation, the less visible the pattern overall is going to be. But the larger I make the number, the more you can see what the real expected value is going to be. I'm starting to see, hey, this guy got 3. That's because we know the expected value of this is take the average. So it's like -0.3 or something like that. So that means this person's getting real lucky. Now, when I change this to be, going towards the hundreds, you can see this game is rigged towards the house. And as a result, you'll see what the graph is left skewed. And so if you're a casino, this is what you want to do. You want to make it to where, now this is, no one would play this game because it's too obvious, but you want to make your game where the expected value is in your favor. Speaking of which, here is probably the most famous example of that. When I first went through this example in my statistics class, it just blew my mind. How can something so, it seems like by doing nothing, you can change the outcome. It's crazy. So there's a game show. This is a real thing. It's a game show called Let's Make a Deal. And on this game show, they had a particular I don't know if this is the only thing they did. Surely not. You can't make a game show out of doing nothing but this. But they have 3 doors. And the idea is you as the participant come up and you're going to pick. One of the doors has a car behind it, and the other 2 have goats. And so if you pick the right door, well, you get what's behind the door is the thing. 3 doors, 3 outcomes. Thing is, the host knows what's behind each door. So the host knows that there's a goat here, and a car here. So what will happen is the host will ask you, after you've picked a door, if you want to change to another door. Now, what the host will do is open another door. So let's say I pick door 1. So the host, knowing that there's another goat over here, is going to open this door so I can see that there's a goat. And then I have the choice. Do I stick with door 1 or go to door 2? So the question becomes, do you change the door? Do you change your position after the host shows you the empty door? Well, first thing we're going to do is simulate this in Python so that you can either do the math, you can go with your gut feeling, or you can simulate it, which is kind of doing that possible worlds thing I was talking about at the beginning, and then you can see the actual outcomes of it. That way you can know what the best thing to do if you want a car, at least. So we've got a function. What does it do? Well, if the string that comes in is goat1, return goat2. If the string that comes in is goat2, return goat1. Very simple. All it does is lets me get the other goat. So I've got 2 goats. If I see one goat, I want this function to tell me the other goat. All right. Next thing we're going to do is we are going to make a list for what's behind the doors, and we're going to make a list for the goats. We're going to shuffle up the doors and pick. If the user guesses the first goat, whichever that is, you can make it left to right, right to left, whatever you want. We're going to give back this list here, which says that the user guessed is goat 1, and then goat 2 and car. So these are representing the doors. If they guess goat 2, well, goat 1 is going to be at the second door. And if they guess car, randomly it's the ghost, it doesn't matter. What do we get out of this? We get if you imagine there's 3 doors that are actually shuffling in front of you, that's what you get. You get what the user guessed, you get the door that the host says, open this door, and they know what's behind each door, and you get the other goat behind the other closed door. All right. Let's run it, see if it's actually working. Seems to be going. Okay, and what we're going to do is we're going to simulate this 1,000 times. So that's our experiment. Play the game 1,000 times and see what happens. Okay. We're going to use a data frame for this. Shocker. Okay, so we see what it looks like. We were going to make a plot out of this, so that's what we're going to do now. Okay, so now what you see here is in orange, we have what your original guess was, right? And so as you can see, it's random. You don't know what's behind the doors, so it's just a 1 in 3 shot. So you get 333 because we did 1,000 times. Or one of these will be 334. 333 of the car, 331 of the goat, 333 of the other goat. It doesn't make it's no surprise to anybody. If I have a D3 and because that's the same experiment, really. I've got 3 random doors, or I have a die with 3 sides. Same thing as far as what should you pick. Well, it doesn't matter, it's random. But now what we have is in blue is the remaining door. Now, how this reads, if I have my original guess, I've got a 1 in 3 shot of getting the car. I got a 1 in 3 shot of getting the goat, 1 in 3 shot of getting the other goat. But the host lifted a door. Do I switch to the other blank door? Well, it turns out it's statistically beneficial for players to switch the doors because the initial chance for being correct is only 1 in 3. Now, the reason this is so, at least to me, confusing is because you've got 3 doors, right? It doesn't matter if I pick the first one or pick the second one. If I pick the first one and then I switch to the second one, it's the same thing, right? I'm just 1 in 3, 1 in 3. Well, no, that's not what's going on. Because the host knows what is behind the doors. So let's say I pick the first one and then they revealed the goat over here. This is no longer the same game I'm playing. I'm not playing the game of 1 in 3 doors. I'm playing there's a goat over here. And I know there's a car behind one of these two. So I should play that game rather than the 1 in 3 game I originally played. It was at least confusing to me. And as you can see, this is an XKCD comic. Usually they do some engineering or math nerd stuff. And this is just the person. It's like, hey, look, a goat. I want the goat. That's like saying the host revealed the goat and you switched to the door that was revealed because you wanted the goat. Goats can be quite useful. They're the only thing that can get rid of blueberry bushes. Everything else doesn't work. All right, so that's a nice little example. Oh, I suppose I should pause for questions. Has anybody got any questions about the Monty Hall? It's what this thing is called, the Monty Hall experiment. Or anything we've talked about in general, because at least to me, this took me quite a long time to what are goats useful for? They eat everything. They can eat anything. So if you've got a pasture that you want like leveled, it's got weeds and stuff, they'll just go nuts. That, and they make milk, and they have meat. And they're cute. If you like that kind of thing. If each person's data is random, why are the plots so similar? Are you talking about here or above when I was talking about the Russian roulette? Same answer, but it would let me at least contextualize the answer better. About the data. So I'm assuming you're talking here. The reason they are so similar is because we're playing the same game. So everybody in the class line up and you're going to have a roulette wheel in front of you. Well, the thing is, me as the casino, I know the distribution of how that game works. So you can everybody play it, not tell anybody anything, and you're all going to be playing the same game, and it has the same rules and it has the same random chance. So let's say we have a game. Well, let's just talk about the D6 one. That's easy. If I make a game where well, let's just put it this way. I'm going to say 1 through 4, you lose $1. On 5, you break even, and on 6, you get $1. Okay, well, everyone in class is going to play 100 times. Well, let's just say I pick 10 people and you're going to play 100 times. I know that most likely, because I'm in the casino, I set up this game, you're going to be losing money. You have a 4 in 6 chance of losing $1, 1 in 6 of breaking even, and 1 in 6 of gaining $1. So if I run this, I would be shocked to see a single positive number here. So since I know this, what that means is it doesn't matter who's playing the game because it's all random. The distribution for how this game comes out in terms of net with 0 about right here looks like this. So if you come in, you play, you're probably going to get something in this area, which is like -40. Next person comes in, you're probably going to get something in this area. It's like -40. Somebody comes in and they come out with this. I'm going to be just amazed. You played this is essentially you came and played 100 games of Russian roulette and you're with yourself and you're still alive. So that's why they all look similar. It's because the game itself has a distribution. Okay, speaking of games, let's make some. All right. So here we have the actual terms. I should look at this first that I was talking about. The experiment is the occurrence. So when I roll the d6, that's the experiment. What we're simulating is 100 experiments, 6 people, 100 experiments each. That's the simulation. The outcome is whatever face came up, at least in the d6. The sample space is the set of all possible outcomes. So what are the possible outcomes? Well, I can't get ace of spades if I'm rolling a d6. The only possible outcomes are the face with 1 pip, the face with 2, 3, 4, 5, and 6. What's an event? It's a subset of possible outcomes, kind of like an even die roll, 2, 4, and 6. And probability is, as we all know, what is the likelihood of a particular set of events. Okay. Let us code up the Russian roulette game, and we're going to be calculating the probability of surviving. So in one round, you got 5/6, which is almost 83%. What we're going to do is compute the probability of surviving for 2 rounds, 5 rounds, 10 rounds. This is exactly what we were doing before, except we're just adding something that says if there's a 1 in the returned list, you're dead. All right. So we're going to make our for loop and see what happens. Got our data frame. Likelihood of surviving, 0 rounds. This is the best outcome right here. If you ever want to play Russian roulette, here's the way you play it. It's like, okay, let's play. I'm done. That's it. You just don't. So the for loop is showing the number of times we play, the number inside the for loop. So as you can see, the longer you play, the more the likelihood of bang. So the outcome, or that's not right. All probability adds up to 1. So what does that mean? With the D6 example, the likelihood of getting a 6 is the same likelihood of not getting a 1, 2, 3, or 4, or 5. Well, I know 1, 2, 3, 4, and 5 have 1/6 chance. It adds up to 5/6. So what is the likelihood of not 5/6? It's 1 minus 5/6. So what's the likelihood of after playing for 10 rounds of getting your head blown off? It's 1 minus this, which is like 0.84. Here we'll visualize that. So probability of surviving looks like this. Longer you go, less likely. Here's another example. We have a D20. What is the probability of constantly throwing an even number with a D20 for this many rolls? So as you can imagine, well, I don't know. I'll ask you guys. How many even numbers are there on a D20? Okay, how many numbers are there that are odd? Right, so there's 10 odd, 10 even. That's all of them. If the die is fair, then is this the same experiment of flipping a coin? Or is it different? Yes, it is the same. So every time I play the game, I've got the same chance of getting an even as an odd. So here we have the probability being 1/2. And we're going to do this 2 rolls, 5 rolls, 10 rolls, 15 rolls. Now, actually having this, I know this for a couple of reasons. One, I'm a math nerd, and two, I play war games with a bunch of dice. Getting an actual die that is, there's no such thing as a perfectly balanced die, no matter what kind it is. D6. I suppose a D1 could be perfectly balanced, but who wants a D1? Getting a as close to truly random D6 as you can. Those things are expensive. So when you go out and you have a D6, you know, if you have one in the junk drawer or whatever board game you have, odds are it's not fair. But for most cases, it's good enough. So we are simulating a perfectly fair D20. What are the odds of getting even rolls? Well, once I start the number of rolls, it's 1 and 2. And every time, this is the possible worlds thing coming up. Well, I had 1 and 2. I'm going to do 1 and 2 again. I'm going to do 1 and 2 again. And you see it quickly becomes less than 1%. This is actually an exponential growth pattern. I suppose you would call it exponential decay because the amount it shrinks gets less and less each time. Let's visualize that. So yeah, exponential decay or growth, same thing. So if you have a coin that you can flip 10 times in a row and get the side you want, it's probably a cheating coin. What's the probability of at least 1/6 with a D6? I don't know. Just like I unintentionally said it before, but these are the same thing. I'm talking in terms of the experiment that we're doing in Python. We're doing the same thing. What are we doing? Well, I'm making a for loop and I'm plotting something and make a data frame. But what I'm doing is simply putting in the outcome, the probability of what I know our thing is. So here it's 5 out of 6. Possible worlds, 6. What are the worlds in which the gun doesn't go off? 5. Here, what's possible worlds? It's 20. And what are the worlds in which we get a even number? It's 10. So 10 over 20 is 1/2. What do we got here? The likelihood of at least 1/6 is 1/6. How do I know that? It's, well, everything I don't want is 5/6, and 1 minus that is 1/6. Same thing. It's just I'm changing the probability of what we're doing here. So let's try it. It's probably at least 1/6 of the D6. Well, this is 1/6, and this is it's not 2/6. It's 1/6 and then 1/6 again. Basically, what you're looking at here is you lose as the house. You lose the game when the player rolls a 6. So how many times are you going to be comfortable with letting them throw the die? Well, the moment this goes over 5, you don't want to let them play anymore. So if you're the casino, you don't want to let them play the game. You don't want to let them roll the die any more than 3 times. Now, what you do to make that, you can't just say, yep, you're done, because it would be obvious. What you do to disguise it, I don't know. The question is, can you have a perfectly random die from a computer program? That's a very good question. The answer is no. Perfectly random does not exist. It only exists in math world. Well, what do I mean by that? Now, this is one heck of a tangent, but I like this tangent. What I've drawn on the screen. Well, I'll ask you guys. What did I just draw on the screen? Now, very interesting. I have to infer what you are telling me, because technically, what each of you just told me was the symbol 3, which is correct. I drew the symbol for 3 on the screen. What I did not draw is the number 3. The number 3 does not exist in the physical world. What we have is a symbol for it. So let's pretend that off in math world, there's this thing. It's the number 3. We can talk about it. We can reason about it. We can do stuff with it. Well, here is a symbol that we all use that denotes this concept. Here's another one. This denotes this concept. I know in Japanese, it's this, denotes this concept. But here's the thing. This concept, this number, the actual number, doesn't exist in the physical world. Can't touch it. This symbol you're seeing on the screen, well, it's kind of weird because I usually do this on a chalkboard. It's just chalk. It's just a layer of chalk on the board. That's the physical thing you're looking at. Here, it's some pixels. It's pixels arranged in a way. That's it. But we know that that pixel arrangement denotes something. Now, why do I bring this up? Is because truly randomness exists off in math world. You can't achieve it. When I pull up a random number in Python, it's because of an algorithm. So I have an algorithm, and what it is called is a chaotic algorithm. So if you plot it, it looks kind of like this. Like it's very, very, as you go from one step to the next, it is very chaotic. That's what is good for a random number generator. But I still know if I plug in the same value for it, I'm going to get the same output. So you plug in with 2 inputs. One is the seed of the time you call this, and you'll get out the closest thing you can get to truly random. But you cannot implement a truly random algorithm because the algorithm has steps to execute. So no, a truly random, a perfectly random die cannot exist in anywhere except math world. That's the only place it can exist. Hopefully you understood that. But it's a good question. It's a very good question. I'm sure I remember talking about this last semester, so we will at least at one point get to the point of how close is close. And this version, it's how random is random? Like, when is it random enough? That's the $1 million question right there. But when I pull up a random, what we're using here, it's good enough for most stuff. Good enough. Here, we're doing the same experiment. We're just doing it more. So you can see the numbers haven't changed. If I'm, what you would have to do if you're the casino is say, all right, if you want to roll the die, it's a quarter. But every time you roll the die again, it's going to be more and more money to do it, to offset the fact that on the 10th roll, you as the house have a 83% chance of losing money. So we're going to plot this. So yeah, the closer we have to 1.0 is the likelihood of seeing a 6 in however many times I've rolled it. So after I've rolled the die 50 times, if I haven't seen a 6, then something is terribly wrong. I've been cheated, essentially. All right. As you may notice, same kind of framework we've got going on here. What's the probability of drawing an ace at least once with replacement? What that means, this is a very important term here, means you draw a card. And if you didn't get the card you want, you put it back in, you shuffle the deck. So how many cards are there in a deck, standard playing card deck? 52. How many aces are there? 4. So one way of looking at that is, so that's 4 and 52. That's the likelihood of getting an ace. That is also 1 minus 48 over 52. Same thing. So we're going to model our experiment here. 2 tries. What's the likelihood of seeing at least an ace? Well, not very high. Well, the question is, if I keep doing this, will I eventually see an ace? Well, the likelihood goes up. Let's just say that. It is technically possible to play this game forever and never see an ace. That is just very, very, very unlikely. As you can see, the likelihood looks like this. Now, you may see a difference in a pattern like this or like this compared to the one we just saw. It's because just the numbers, what's going in here is all. All right. Let us do this example, and then I'll look quickly at the homework, because in the homework is everything we're doing here. We've got our scaffolding of everything we want to do. Write a function to find the probability of an event in percentage form based on given outcomes in sample space. So this is a lot of terms that if you hadn't done the previous parts of the lab, it would be a little confusing. But we know what they all mean. What's the probability? It's a number. We want it in percentage. So it's going to be something in percentage terms, it's going to be something from 0 to 100%. What's an event? It's any subset of possible outcomes. I could pick whatever I want. So in a deck of cards, I could say an event is either the 3 of clubs or the 9 of spades. Drawing a 3 of clubs is an outcome. Drawing the ace of spades is an outcome. And I'm the one making what the event is, so I choose it. So you're going to be given an event, and we want the probability in percentage based on what the outcomes are and what the sample space is. What's the sample space? All possible outcomes. So with a D6, what's the sample space for a D6? 1, 2, 3, 4, 5, 6. All right, so the first one. These are all the same for the first part, so I'm only going to read the rest. So rolling a 4 with a D6, all right? Drawing a king from a standard deck of cards, drawing the king of hearts from a standard deck of cards, drawing an ace after drawing a king, drawing an ace after drawing an ace, drawing a heart or a club, or drawing a royal flush. Okay. Now you will notice very quickly that these are all the same kind of thing as far as coding it up. We just have to figure out what the probability is. So the first one, well, this is just setting up our percent thing. What's the outcome? There's only one way to get a 4 on a D6. How many total are there? Possible outcomes are 6. Okay, so look at that. This is the likelihood of, in one experiment, getting the outcome we want. All right. So this is really an exercise in you figuring out what are the possible outcomes, or really what is the event. So it's 4 in 52. And what's the sample space? It's 52. There's 52 cards. Right? Same thing here. It's 1 in 52. Now, this may seem like, oh, well, this is easy. I'm just dividing this number by this number. That's not the exercise. The exercise is you figuring out these numbers. They're already written here. They won't be in the homework, but yeah. Now this one, you notice that there's 51 cards left. It's because the only way for you to get a card after drawing another card is to not put it back. Okay. So this is the number of hearts, spades, or hearts and clubs, the total number of cards in the deck. And so we have the probability of one or the other is the probability of one plus the probability of the other. And this is the final one. Okay. The rest of these are just encodings of what is written here. It's really simple to just run them and you'll see. What's probably rolling an even number and greater than 7? Well, you can see it's about 25%. Probability of drawing 3 white and 2 red balls out of our sample space is about 5.5, so on and so forth. So let's look at the take home. You're going to get a CSV with concrete data. And here's what we're wanting you to plot. There. Sorry. So if you run this, it's going to have all that image, and the idea is for you to this isn't a lab about plotting. This is a lab about determining correlation and values and probabilities. So we want to get the correlation coefficients on here. I'll show them again. Oops. Let's see here. It would be helpful if I did it in order. As it plots, it's busy, you can see here. Well, eventually they'll pop up. And what you need to do, there it is. We need to determine the correlation coefficient, rank the predictive value of the variables, highest magnitude to lowest value, so on and so forth. The fifth one is, it's not something you code up. It's did what you do, did the things you did accomplish what you wanted to do? And then just like before, just like that one, this is something you answer. You can either make it a comment or you can change it to Markdown, whatever you like. Okay, so we are right about at the time. So any questions, comments, or concerns, or anything else for that matter? I did get quite a few emails about the exam. I'm more than happy to like talk about concepts that you want to, like if you want to go through stuff with me to study, that's fine. But as far as particulars and submissions, I don't handle that part, so I can't really help you. I do have the recordings for the last week's lab. I will get them up on Blackboard in a way that either I'll find how to do it exactly how Dr. Cleveland did, or I will put them in a spot where he can do that. So other than that, yeah, that's pretty much all I got. Lab 17, a week from when it was assigned. So that was Monday, wasn't it? Which would be tonight. It was either Monday or Wednesday. I can't remember. I can't remember what I had for breakfast. Actually, I had coffee. Okay. That's all. I will see you all either Wednesday or tomorrow for office hours.